Welcome to the second video in a series of 4 about the unit circle. Here we'll study the 6 trigonometric functions. 6 trigonometric functions are cosine, sine, tangent, secant, cosecant, and cotangent. We'll get into what all these are, but first it's worth noting that you see some duplicate root words in here. And I would recommend at the beginning of this topic, which you may be in right now, that you not try to associate sine and cosine with each other, despite the fact that they sound similar, or tangent and cotangent, again, despite the fact that they both have the same root word. Likewise for secant and cosecant. Now, there is a connection between them, and there is a reason why some of them start with co and some of them don't. But that's something that you have to get pretty far into trigonometry to have a profound understanding of. So for now, I wouldn't try to draw any connection between these root words. We're going to start this video by studying the two most basic of the 6 trigonometric functions, cosine and sine. We'll start with cosine. Here's the definition of cosine. I'll be quiet while you read. Now, those are some confusing words to most students, and it is kind of the way that mathematicians speak. It takes a while to get used to that, if one ever does. And so what I've done is I've converted this definition into more of what I call an action-based definition. So I'll read it to you as you track along. If you want to find the cosine of some number, what you do is you create an arc of that length, find the terminal point, and take the x-coordinate. Now, these two definitions are the same. The one on the left is in mathematician language, and the one on the right is in I want my students to get good test scores language. Both have some value, obviously. So, that being said, we'll use the definition on the right to do this example. We're going to find the cosine of 2. So, looking in the directions on the right, we have to create an arc length of 2. I'll remind you how that works. Here's our initial point with an arc length of 0, and an arc length of 2 goes out to there. Why? Why is that a length of 2? Well, you'll remember that in the unit circle, the radius is 1. So that length of that arc is about 2, and that's why I stopped approximately where I did. Second, in my definition, my action-based definition, is I've got to find a terminal point. Well, there it is. Okay, easy enough. Step 3, I need to find the x-coordinate of that point, and that will be the cosine of 2. Well, watch the diagram. If I were to project down to the x-axis, whatever this length is, wouldn't that be my x-coordinate? Or negative that length, I should say. So then now we have to find that length. Well, it turns out that that length is about 0.42. How did I know that? I typed the cosine of 2 into a calculator, and I approximated. Okay, fair enough. Now that I know that that length is about 0.42, then the terminal point must be negative 0.42, comma something. I don't really care what the something is, because I'm trying to only find the x-coordinate of this point. And since the x-coordinate of that point is the cosine, I now know that the cosine of 2 is approximately negative 0.42. Now here's a subtlety you may have thought of. Why on earth would I need all that unit circle work? Why would I even need the action-based definition or the mathematical definition at all? If a calculator will find the cosine of 2 for me, why do I need any of this? Well, to find the cosine of 2, you really need a calculator. Well, unless you would do what they would do in the pre-calculator era of mathematical history, which is where they would physically build a unit circle and wrap a string around it whose length was 2. Short of doing that, why can't we just rely on a calculator to do all the problems for us? Well, it turns out that there are problems that you'll be expected to do without a calculator, but you can't do the cosine of 2 without a calculator. So what problems will you be expected to do without a calculator? You'll be expected to do any r value that terminates on one of the 16 favorite points of the unit circle. With that being said, let's look at an example of something that you would have to do without a calculator in a mathematics course. Okay, suppose we're trying to find the cosine of 5 pi over 6. Let's go through our action-based definition in the upper right corner. We need to create an arc of length r. Here's my unit circle. Here's this initial point. And r in this case being 5 pi over 6, I've now created an arc of length 5 pi over 6. Now you might stop and ask, how did I know that that arc length has a length of 5 pi over 6? How did I know to stop where I did? Well, here's a good mental trick. Think of 5 pi over 6 as 5/6 of pi, or alternatively, think of it as 5/6 of the top half of the unit circle. So I stopped at my terminal point when I was about 5/6 of the way through the top half of the unit circle. And that is the best way to think of 5 pi over 6, in my opinion. So now, looking at our action-based definition in the corner, we now have to find the terminal point. Well, there's the terminal point. Now, you may recall from the first video that we write the arc length at the terminal point. It's just a convenience thing. Remember, we're not calling that point 5 pi over 6. We're writing 5 pi over 6 there because the arc terminates at that point. That is the arc length. Now, I found the terminal point. Back to our action-based definition, I now need to find the x-coordinate of that terminal point. So here we go. Watch the point on the unit circle. If I were to project down to the x-axis, finding the x-coordinate is equivalent roughly to finding the length of that segment. You may see it as green. How am I going to find that? Well, you may recall from the previous video that when we have any multiple of pi over 6, the terminal point on the unit circle forms a 30, 60, 90 triangle within that unit circle. You may also recall that the lengths of the legs, you may see them both as green, the lengths of the legs are always radical 3 over 2 and a half. Now, we went into extensive detail last video about why these are always the lengths of the legs of a 30, 60, 90 triangle whose hypotenuse is 1. And if you'd like to go review that, you should, but I kind of have that committed to memory, so I won't go through the derivation of that again. But here's the bigger question. Even if you do remember that, which one of these is a half and which one of these is radical 3 over 2? Well, one clue that you can use to answer that question is to remember that we're in the unit circle. And this segment here, you may see it as blue. This segment on the right has a length of 1. So now looking back on the segments on the left in green, which one of those do you think has a length of a half, and which one has a length of radical 3 over 2? Before I answer, it's also worth memorizing that radical 3 over 2 is about 0.87. Now, if you're doing this problem without a calculator, you wouldn't know that, but it's a number that comes up so often, it's really worth memorizing the decimal approximation. And now if you look back at the two green segments, it's pretty clear which one has a length of 0.87 and which one has a length of a half. So now that I know the lengths of those legs, I now know the coordinates of that terminal point. And notice that it's negative number, comma, positive number, because we're in quadrant 2. Now recall, step 3 of our action-based definition was to find the x-coordinate of the terminal point. Well, we now know the terminal point, and now we know its x-coordinate, and we're done with this problem. And we have found the value of the cosine of 5 pi over 6. Well, even though I'm done with the problem, there's a comment I'd like to make. It's very typical for students to ask me the following question, and I think that this will help you going forward in trigonometry. The students ask me, hey, Mr. Rasidlo, why do I need to go through all of that thoughts of 5 pi over 6 and the 30, 60, 90 triangle and that whole discussion that we just had? What is the value of any of that? If I just memorize the entire unit circle, then I'll know where 5 pi over 6 is. And if I memorize the coordinates of that point, as shown here, then I don't have to go through the thought process that I just spent 5 minutes on to find out that the cosine of 5 pi over 6 is negative radical 3 over 2. If I just memorize the coordinates, then I'll know the cosine is the x-coordinate, and I'm done. Well, a student who would ask me that wouldn't be wrong. Here's the problem with that logic. You can't spend your whole education career walking around with the unit circle memorized. And there are going to be moments where you need to know the cosine of 5 pi over 6, for example, in a calculus class, without having the unit circle memorized in your head. If you could walk around with the unit circle memorized forever, then that would be fine. But it's not typical for most humans to be able to do that. So the value of going through the process of thinking, where is 5 pi over 6? Oh, it's 5/6 of the way through the top half. And what are the x coordinates and maybe y coordinates of that point? Well, they have to be radical 3 over 2.5, and then using deductive reasoning to figure out which is which. That entire process, if you approach the problems that way, then you won't need to memorize the unit circle, and you will be able to answer questions like the cosine of 5 pi over 6 without pure memorization. And that is of much longer term value than any kind of shortcuts one could find on these kinds of questions. Again, it's not reasonable to memorize the unit circle. All right, so we're done with this problem, and now we're going to move on to the second of the 6 important functions, the sine function. So the sine function is defined very much like the cosine function. I'll let you read that. The only difference between sine and cosine is that the sine is defined as the y-coordinate. So again, because this is kind of mathy, I'll put an action-based definition here, much like I did before, to show you the steps to go through to find the sine of a particular value without a calculator. So here's our example. Let's find the sine of 5 pi over 4. First, I need to create an arc whose length is 5 pi over 4. Here's my initial point. Here's an arc whose length is 5 pi over 4. Now, to help you understand why I stopped where I did on that arc, think of 5 pi over 4 as 5/4 of pi. 5/4 is the same as 1 1/4. So think of it as 1 1/4 of the top half of the circle. In other words, it's more than the top half of the circle. It's 1 1/4 of it, or an extra quarter if you want to think of it that way. So now I've got to find my terminal point. Well, there's my terminal point. And remember, we write the arc length typically at the terminal point, even though it represents the length of the entire arc. And now I've got to find the y-coordinate of that point, and that will be the sine of 5 pi over 4. Now, watch the point. If I project to the x-axis, then wouldn't the length of that projection be the y-coordinate? At least with a negative. And so I now want to find the length of that distance. Well, Remember from the previous video when we studied multiples of pi over 4 in depth? Remember how they all correlated to a 45, 45, 90 triangle inside the circle. Or to restate that, we concluded in our previous video that whenever our terminal point corresponded to an arc whose length was a multiple of pi over 4, that the lengths of the two legs were both radical 2 over 2. And if you want to see a full derivation of why that is, take a look at the last video. It goes into quite a good amount of depth to explain that. But I generally tend to just commit that number to memory as the length of the legs of the triangle that corresponds to a arc whose length is a multiple of pi over 4. And so having committed those to memory, it's pretty easy to see what the coordinates of this point is. I just put a negative in front of the x and y coordinates because we're in quadrant 3. Of course, both of those would be negative. And so now that I know the coordinates of that point, remember I want the y coordinate of that point to be the value of my sine function, and therefore I now know the sine of 5 pi over 4. Now again, most students will ask me at this point, Professor Rasidlo, why do you go through so much trouble of drawing the unit circle and finding the triangle inside of it and analyzing as the 45, 45, 90 triangle and all of that? Professor Rasidlo, couldn't you just memorize where 5 pi over 4 is on the unit circle, memorize the coordinates, and then when you're asked the sine of 5 pi over 4, you simply pull out the y coordinate and you're done? Again, there's nothing wrong with that, except that it's impractical to memorize the unit circle. I've found that because I memorized a process rather than just facts, I can recall points on the unit circle. I shouldn't even say recall. I can find coordinates of points on the unit circle by deduction and reasoning, and I don't have to memorize them. I think that's of much greater value than memorizing the unit circle for a quiz and then forgetting it the next day. Let's move on to another example. Let's find the sine of negative pi. So let's go through our action-based definition on the right. Here's the unit circle. Since we have a negative pi or a negative arc length, we're going to go clockwise. And a distance of pi is half the circle. So here's my terminal point. And that point, by the way, is negative 1, 0. Didn't have to go through a lot of trouble to find the x and y coordinates of that point. In case you forgot why that point is negative 1, 0, might I remind you how small the unit circle actually is, and that the point in question is right here at, as you can clearly see in the graph, negative 1, 0. And remember, because I'm finding the sine of negative pi, I want the y coordinate of the terminal point. Y coordinate of the terminal point is clearly 0, and therefore the sine value is 0 at negative pi. So now let's go back to what our original plan was. We're here to look at the 6 trigonometric functions. Up until now, we've looked at the cosine and the sine. And those, it turns out, are the main two in the sense that, one, they were the most commonly used, but further, in that if you can compute those two, it's real easy then to compute any of the other 4. So next, let's take a look at tangent. Here's the definition of tangent. Here's the action-based definition, telling you exactly what to do to get a tangent. Essentially, you find the sine and the cosine, and you divide, and that's the tangent. Here's an example. Let's find the tangent of 7 pi over 6. Here's my initial point. Here's an arc of length 7 pi over 6. We'll put the length at the terminal point. Just to give you a proper perspective on this, you might wonder, why did I end the arc there? Well, think of 7 pi over 6 as 7/6 of pi. But 7/6, that's 1 1/6. So think of that as 1 1/6 of the top half. In other words, the full top half plus an additional 1/6. So now that I have my terminal point of 7 pi over 6, let's remember how multiples of pi work. Multiples of pi lead to 30, 60, 90, multiples of pi over 6 lead to 30, 60, 90 triangles. And I won't explain exactly where these leg lengths came from, but I did explain that earlier in the video. If you need to rewind to that point, you may want to do that. But once you realize, oh, I have a multiple of pi over 6, and so I'm going to have these as my x and y coordinate, then you know what the coordinates of that point are. Notice I put two negatives here because we're in quadrant 3. Of course, all coordinates in quadrant 3 are a negative number, comma, a negative number. But now that I know the coordinates of that point, let's get back to our plan. We need to define the sine of r first. The sine of r is the y-coordinate of that point. We need to define the cosine of r. The cosine of r is the x-coordinate of that point. Those are both by definition. That's the definition of sine and cosine. Now all I have to do is divide. So what I did is I divided on scratch paper. It was very messy. Many, many steps later, I got my final answer. And that's the answer to the tangent of 7 pi over 6. Before we go on to another example, however, I'd like to show you my scratch paper. Here's the division. And hit pause if you want to analyze the details. So when I divided the y-coordinate by the x-coordinate, or the sine divided by the cosine, I got 1 over radical 3. In some courses, the teacher or professor will let you stop there and say, there, the answer is 1 over radical 3. In other courses, teachers and professors will want you to rationalize the denominator. In other words, not allow radicals in the denominator. So if you're in such a course, here's the work that shows the rationalization of the denominator. Again, hit pause if you want to analyze the details. And now we're going to take a look at a second example. Let's look at the tangent of pi over 2. Here's my unit circle. Here's an arc of length pi over 2. You may recall that this is a quadrantal angle. Here's the terminal point. That point is 0, 1, as we've discussed a few times before. But now let's look at our action-based definition in the corner. We need to find the sine of r, or pi over 2 in this case. And that's 1 because it's the y-coordinate. We need to find the cosine of pi over 2, which is 0 because that's the x-coordinate. And now I just need to divide. So here's my division. Problem is, 1 divided by 0, or anything divided by 0 for that matter, doesn't exist. Some teachers use the word undefined. Mathematicians decided centuries ago that division by 0 was not going to be an allowable operation. There's a whole other story behind that, but I don't want to get sidetracked. And therefore, the tangent of pi over 2 does not exist. And again, some teachers would say undefined. If something doesn't exist, then we can't define it. Same logic. So back to our overall progress. This video is about the 6 trigonometric functions. First, we studied sine and cosine in detail. We just finished 2 tangent examples. But if you can do cosine, sine, and tangent, you can very easily do the other three, the secant, the cosecant, and the cotangent. Here's why. It turns out the secant is, by definition, 1 divided by the cosine. The cosecant, similarly, is defined as 1 divided by the sine, and the cotangent is defined as 1 divided by the tangent. There's no reason for these. These are the definitions of those three functions. If you're wondering where they came from, that's a whole other story. As far as you're concerned, those are the definitions, and that's how they've been defined. Now, for the cotangent, a shortcut, not a definition, but a shortcut is the cosine divided by the sine. And that gives you the same result. So, I'm not going to do an example in this video. There's no reason to clutter your brain with more information at this point. But suffice it to say that the last three are easy to calculate if you can do the first three. For example, if I were asked to do the secant of 3 pi over 4, I'm not going to do it here, but if I were asked to do that, I would find the cosine of 3 pi over 4, and I'd get some answer. And then I would do 1 divided by that answer. That's the definition of secant. Similarly, if we were going to look at the cosecant of 11 pi over 6, again, I'm not going to do that here to show the answer, but if I wanted to know that, I would have to find the sine of 11 pi over 6 first. And then whatever answer I got, I would then calculate 1 divided by that answer. And similarly for cotangent, if we wanted to do a cotangent problem, we would do the tangent problem, get an answer, and do 1 divided by that answer. That's how you compute the last three. These are sometimes called the reciprocal trig functions because they're the reciprocals of the first three. It wouldn't be proper for me to end this video without telling you that mathematicians never write out the full word as you've seen me do in this video. Notice the abbreviations on the right. You may see them in red. So for the rest of the video series, I will not write out the full words of any of the trigonometric functions. Rather, I'll simply use their abbreviations. And that completes the second of 4 videos in this series.